Okay, we are continuing on chapter 14. And as we talked about last time, we are heading into some of the more difficult information here in chapter 14. So previously, I believe we finished up talking about really titrations of polyprotic acids, guys that have multiple hydrogens that come off. As we talked about, they do come off again one at a time. And each hydrogen that comes off will have a Ka value associated with it if it's obviously a weak acid we're dealing with. And in that situation, as we saw, we went through a calculation where we really calculated the equilibrium concentrations pretty much of everybody going through all three hydrogens coming off. But what we really saw was, as we talked about, as you go from, say, the first hydrogen to the second or to the third in the case of phosphoric acid, like we did in the example, it does get progressively harder to remove those hydrogens as one comes off. And we saw that with really the concentration of H plus in, say, the second step and the third step. I forget what it was at the end there, but it was like almost to like the minus 16. So really nothing came off very much in the second or third sort of hydrogen. And as we talked about, if it is just a question where all you're interested in is the pH of that polyprotic acid, and you could pretty much in most cases safely calculate the pH just based on the first ice table basically, and the amount of H plus that comes off, as again, not very much comes off after that point. Any question on that stuff that we talked about? We also talked about obviously salts, I think, doing some calculations with salts, and any questions like that? Okay, so what we're going to get into is what is known as the common ion effect. It really is sort of what happens, and we'll talk about it in a second, in a buffer situation. So the common ion effect is the idea of is when you have an ion that is in common with a weak acid or base or weak base. And the presence of that common ion, what it will essentially do is it will suppress the ionization of the weak acid or base. So basically the presence of the common ion will keep that sort of weak acid or weak base really together. And it's sort of based on really Le Chatelier's principle that we talked about. The presence of those guys together will cause a uptick really in the product side and cause the equilibrium really to shift to the left there and keep everybody basically together. So an example of this, you know, if we just look at a weak acid like, not those guys, there you go. If we take a look at a weak acid like acetic acid, when we have acetic acid, when it's in solution, it will set up an equilibrium that will produce acetate and some H plus. So now if we had a beaker where we did dump in some acetic acid in there, it would obviously set up this equilibrium. Now, if we take that same beaker and we dump in some acetic acid and we dump in something like some sodium acetate in there with it, into here. Sodium acetate is a salt, and as we know, a salt will pretty much break apart. So when we have sodium acetate in solution, it will not stay together. It will 100% break apart into sodium ions and acetate ions. So basically, when we dump both of these things into the solution together there, it is going to A, set up this equilibrium, and B, generate these ions in solution in that beaker. Now, when we look at the only one that will set up an equilibrium, which is our top equation here, that is coming from the acetic acid, what we're essentially doing when we add the sodium acetate is adding more sodium, adding more acetate in this case. And based on Le Chatelier's principle, by adding to the right, it should shift away from it, and we should see a shift in the equilibrium to the left. Any questions on that there? Obviously, the sodium is still floating around, really not doing much. It's just kind of hanging out. By doing this, this affects something like pH. How would that affect the pH in this case? Would it be lower the pH? Would it be higher? What do you think? It is a 50-50 shot on that, you know, up or down. Yes, take a guess. I heard up and down. That is both guesses. That's good. So let's think about first off, what affects the pH, right? The pH is minus the log of the H plus concentration, right? When this equilibrium shifts to the left, will I have more or less H plus? I should have less, right? So H plus is over here, right? So as it shifts to the left, I should actually end up with less H plus. Less H plus means that actually the OH minus concentration goes up, and we would actually expect the pH here to go up. Probably maybe not basic or anything like that, but it should be higher in terms of pH than if we just had the acetic acid by itself without the acetate present in that particular case. Any questions on that? So having the presence of the common ion, that's what it means when it talks about it suppressing the ionization or dissociation of the acid. It's basically keeping this guy together, because really the definition of an acid is the ability to release that H plus into solution. So with it staying together, we're going to have less free H plus in the solution. And what we'll see is, you know, we'll see a higher pH than if we just again had the acetic acid by itself. Any questions on that there? And again, that's what we see here, that presence of that acetate causing the equilibrium again to shift to the left, less H plus present at that point, and we would see the pH come up a little bit from just the acetic acid by itself. So why don't we take a look here at one of these here, or both of these. So why don't you do A first, and then we'll talk about it, and then we'll kind of tackle B here together. So what is the pH of a 0.2 molar acetic acid solution? Ka value of acetic acid right there. So take a couple minutes, see what you come up with. I calculate the pH of a 0.2 molar acetic acid solution. Again, remember, there's a lot of information in the problem. So that's acetic acid. You weren't sure what type of acid, that should immediately tell you that this is a weak acid. And again, that should immediately tell you should be doing an ice table in this situation. This is really just like a Ka problem that we did earlier on in this chapter. So that is where we will start. So we will take our acetic acid here. We will dissociate it into a little bit of acetate here and some H plus. That is going to equal our Ka value of 1.8 times 10 to the minus 5. We're going to do an ice table like normal. So it was 0.2, I believe. And again, we would do 0 and 0 here. Change would be minus x, plus x, which means at equilibrium 0.2 minus x, and x. Any questions on the ice table here? This, like normal, will go into our Ka expression, which in this case is our products divided by our reactants. And that would equal our x squared, basically, divided by 0.2 minus x equals 1.8 times 10 to the minus 5. I'm going to go and assume here that x is equal to 0 as we have a small value for k. That will get rid of that x right there and give us x squared divided by 0.2 equals 1.8 times 10 to the minus 5. We're going to multiply this guy to the other side and also take the square root of it while we're here. So we're going to take 0.2 times 1.8 to the minus 5, and again, come back and take the square root of that. And looks like we end up with an x value of 0.001897. I believe somewhere in that ballpark. At that point, we do want to check it, so we can divide it by 0.2 and times it by 100%. And I think the check is good. I think it's like 0.9%, something like that. So that does mean that this would be our H plus concentration, 0.001897, which now we can go into our pH. And again, we know that from looking at our table that that is the H plus, minus the log of 0.001897 opens us up here with an opening pH of 2.72 here for this weak acid. That is obviously an acidic pH, so that's good at least, right? If it was 12, that would be not so good in that case, yeah. Any questions on any of those steps? So this is really just a basic Ka problem like we did earlier on in this chapter in this particular case. Any questions? All right, so then let's look at part B here together. And part B is a little bit different. We are using really the same weak acid here. So we're using the same acetic acid with a 0.2 molar concentration. But in part B, we are also dumping in there 0.3 molar sodium acetate. So in part B, they are both basically going into the exact same bucket here, if you will. And again, out of these two, one is a salt, which is basically a strong electrolyte and will 100% break apart. The other one, obviously, as we just saw, is a weak acid, which will set up the equilibrium. So in this case, it's always going to be like your weak acid or your weak base that's going to set up the equilibrium. And this is going to be a common ion. Again, it is the, as we saw earlier, it is going to be that acetate that's going to come from the sodium acetate that will be our common ion in this particular case. So the way that we approach this to calculate it is we can do an ice table, and it would be the exact identical ice table to what we just did there. Again, because the acetic acid is the only one that will set up that equilibrium. So why don't we take a look at that? So using our same ice table here. And obviously we would use our same Ka value because same guy. Now, initially we have 0.2 molar of the acetic acid. We have 0 of the H plus. And because this is a common ion, we actually do have acetate in there, right? So we have that acetate floating around. So the importance to doing this when you do an ice table is you need to have an initial concentration of the acetate that is coming from the sodium acetate. So if this guy is 0.3 molar, what would be the concentration of the acetate? It would be 0.3. It's a 1-to-1 relationship. So that is a very important part, and a part that frankly people screw up all the time on when they decide to do an ice table here is they're so used to putting 0 over here on the right that they zero it out. But in this particular case, we actually do have an initial concentration of the acetate that again is coming from the sodium acetate. That is what is basically providing that initial concentration. Any questions on that part? So that's really important in a common ion problem and really a buffer problem. If you choose to do an ice table, you got to have numbers on both sides. Otherwise, if we zero it out, we're essentially just doing the exact same calculation we did previously, right? Which is just the weak acid calculation. The rest of the ice table is actually identical. So minus X, plus X, and plus X here. That means at equilibrium, we got maybe 0.2 minus X, X, and 0.3. The other place where people screw up is right here. This is a plus X, not a minus X. So again, a plus X in that case. Any questions on that ice table? So that is the difference here, obviously, between the weak acid by itself and the weak acid that has the sodium acetate contributing that common ion in this case. Rest of it works the same way. We're going to go into our Ka expression, which is really the same expression as we had on the previous problem there. And that would get us x times 0.3 plus x up on top, divided by 0.2 minus x on the bottom, equals 1.8 times 10 to the minus 5. Just like I did on the previous one, I'm going to assume that x is equal to 0 here. And again, we will only be getting rid of the x's we're adding or subtracting from a number, basically. That will then get us to x times 0.3 divided by 0.2 equals 1.8 times 10 to the minus 5. So we're going to basically multiply the 0.2 to the other side and come back and divide by 0.3. And that is going to get us an x value of 0.000012. Again, in this case, you could check it, you could divide it by 0.3 times it by 100%. And again, I think we are good on that. You're not even 1%, I think. So much like before, as we go back to our ice table, we do see that X is actually the H plus concentration at equilibrium. So once again, this does equal our H plus concentration, which means we now could go into our pH, which would be minus the log of that number. And looks like a 4.92 at this situation. Any questions on that part? Did we see what we expected to happen if we compare the weak acid by itself to the weak acid that has the common ion? Which one had the higher pH? This one here with the common ion. So we do see Le Chatelier's principle occurring here when we just look at the pH values of those two. We went from 2.72 with the acid by itself to, because of this common ion causing the equilibrium to shift this way, the amount of H plus gets less. And we do see that obviously the pH was a little bit higher than it was in the case when it was by itself. Any questions on any of that there? Okay, so these are common ion problems, and as we'll talk about in just a second, they really are what are referred to as buffer problems, and we'll talk about what buffers are in just a second. Now, in problems where that involve sort of common ions, if we start with sort of a relatively good concentration of our initial parts, the weak acid and the salt, or even the weak base and the salt, we actually see that at the beginning and the end, the concentrations remain pretty much the same. So in this situation, in a lot of situations, the initial concentration of your acid and your salt will be the same as the equilibrium concentrations of each of those guys. And we can see that very simply by going back to our table here. Our initial concentration of the acid was 0.2. If I take 0.2 and subtract this number, I think here if I take 0.3 and add this number on the bottom, which is our X value, with pretty much 0.3 as well. So there is a little bit of change that occurs. Again, we got two things happening here that makes the change be relatively small. First off, it's a weak acid or base, which just by that definition means most of it's staying together. We compound onto that a common ion, which is also going to shift it to the left a little bit more and keep everybody together. We get a relatively very small change that occurs when we're dealing with common ions. So what does that mean? It means that, frankly, you can avoid doing an ice table in a situation like this if you would like. And you could use the David Hasselhoff equation, now the Henderson-Hasselhoff equation here. Henderson-Hasselbalch, which is the pH is equal to the pKa plus the log of the base over the acid concentration. The pKa value is equal to minus the log of the Ka value. So this is the Henderson-Hasselbalch equation. It is really specific for really only common ion situations, which are really buffer situations, is really where you should use this equation. As we'll talk about as we continue through this chapter, you should not use this equation in every situation, but people will want to use this equation in every situation where they end up with two numbers. You go, cool, I got two numbers, I need two numbers, seems like a winner. And it will be a loser in a lot of situations. Yes, so it has to be a buffer situation, really, or a common ion situation, which is really the same thing to use this. So if we look at that situation that we were just dealing with, which is, go back here, we'll do it this way here. So we had acetic acid, which was 0.2 molar. We had sodium acetate, which was 0.3 molar, and we had a Ka value of 1.8 times 10 to the minus 5. If you could recognize both of these things as basically being related to each other, and here we see our common ion, we could go directly into the Henderson-Hasselbalch equation. So the first thing you would want to do is calculate the Ka value, which would be minus the log of the Ka, which is minus the log of 1.8 times 10 to the minus 5, gives you a 4.74 as the pKa value. We then could go into our pH, which would be the pKa, our Henderson-Hasselbalch equation, which would be the pH is equal to the pKa, which I'll just write the actual number there since we just calculated it, would be good. Which in this case would be 4.74 plus the log of the base. Between the two ones that I boxed, which one's the base? Which one's the acid? It would be the guy on the left, which is known as acetic acid, yes? The base would be the other guy. So typically in this situation, your base has one less hydrogen, because an acid will donate the hydrogen, right, to become the conjugate base. And also will usually be carrying some type of spectator ion, like a sodium, a potassium, something like that. But again, the acid obviously would be the one that's associated with the Ka, or has the extra hydrogen, and the base typically obviously will have one less hydrogen in this situation. That means what we want to go on top is the 0.3 divided by the 0.2. And again, if we go 0.3 divided by 0.2 and then take the log of it, add it to 4.74, gives us a 4.92, which is exactly what we got by doing the ice table. So this is a nice convenient way, and probably a quicker way, maybe less room for error than doing an ice table. But a couple of things of note is you could absolutely do the ice table. So if you like the ice table, you're not sure you should do this equation or whatever it may be, can't remember this equation, you can always do the ice table. But again, you could only use the Henderson-Hasselbalch equation here in a really buffer situation or a common ion situation. Any questions on that there? Now, there is also a sort of POH version of the Henderson-Hasselbalch equation, and that is the POH is equal to the pKb plus the log of the acid over the base, where the pKb would be minus the log of the Kb value. Now, sometimes people will use this equation in a basic situation. I personally think it's kind of a waste of time, because in most cases you're asked for the pH, which means if you use this equation, you got to subtract 14 at the end to get yourself to the pH. when you could just as easily go into the Henderson-Hasselbalch equation in a basic neutral acidic situation. It really doesn't matter as long as you're using a pKa value and the base over the acid. So sometimes you will see people though use sort of this to calculate the POH, but in most cases you're looking for the pH. A nice relationship though between pKa and pKb is if you take the pKa value and you add it to the pKb value, it equals 14. So this is also sometimes helpful for you if you want to stick with going with the Henderson-Hasselbalch like this guy, which I would recommend. And maybe you are dealing with a weak base and you have only a Kb value given to you. You could calculate the pKb, subtract 14, that will give you your pKa, and then you could go into your Henderson-Hasselbalch equation pretty easily at that point. So those are some useful relationships. This one. And again, I guess that's a good one too. But personally, for my money, I would shoot into this one most of the time, if not all the time, because like I said, you typically will want the pH. Yeah, either of these equations here, which is really the guy on the right as well, which is the Henderson-Hasselbalch equation, should only be used in a common ion situation. And those common ion situations we're going to talk about in just a sec are really buffers. So you can obviously make a buffer that's acidic, basic, or neutral. So the pH equals the pKa plus the log of the base over the acid works for any pH type of solution that you'll come across. So yeah. Other questions? Okay. So why don't you give this one a go here? What is the pH of a solution that contains 0.3 molar formic acid? I'm going to go with, and 0.52 molar potassium formate. The Ka value is 1.7 times 10 to the minus 4 for formic acid there. Okay, let's take a look. So we have a Ka value, which tells us this is a weak acid. So one thing that we know should be happening is this guy will basically set up an equilibrium. This guy over here is a salt in this case. And again, that means it is going to 100% break apart there in solution into a K plus and some formate in this case. That means that obviously here, the common ion would be our formate that we have here. So if you chose to do an ice table, again, it would be based off of the formic acid, setting it up, and you would have 0.3 molar here, 0. And again, the potassium formate is going to supply 0.52 as it is a one-to-one relationship. The change would be minus x plus x plus x. And that would give you 0.3 minus x, x 0.52 plus x. This would go into your Ka. You would solve for x. X would equal the H plus concentration, and then to your pH. Alternative to that, again, is you recognize that you have really a common ion situation happening here. We could skip all the ice table part and go directly into the Henderson-Hasselbalch equation here, where we would calculate our pKa value as minus the log of the Ka, which would be 1.7 times 10 to the minus 4. Let's say 3.77. Sounds like a winner, maybe. Sounds good. 3.77. We go, the pH would equal 3.77 plus the log. The base here again would be this guy, right? As this is obviously our acid that goes with our Ka value. So we would want to go 0.52 up on top, 0.3 on the bottom there. We want to divide those guys first, and then take the log of it, and then add it to 3.77, giving us a 4.01 as our pH. This obviously is an acidic solution here, And obviously here you should end up with the same pH if you went through that route. Either one is a perfectly fine way of doing it, whichever way you feel more comfortable doing it, but you don't think you will mess up. Any questions on it? Yeah. Say it again, how would you find
which polarity to use for the
of this guy over here?
yeah.
Yeah, so it does come from here, from the potassium formate. So and when that would break apart in solution, you have the HCOO minus plus K plus. This guy was 0.52 molar altogether. It's basically a 1-to-1 relationship between these guys, which means it would be 0.5, and it would also be 0.5 for this guy as well. And that's really because if you do sort of the long calculation of it, that's moles of HCOOK over liters, and it is a 1 mole, right, of the whole thing to 1 mole of the HCOO minus, and that ends up with 0.52 moles of HCOO minus per liter. That's why we say multiply by 1. It's basically a 1-to-1 relationship. Yeah. Obviously, if it was a 1-to-2, you would multiply by 2 and so forth. Yeah. Other questions? And again, it is that supplying a sufficient amount of the formate in that solution. This guy by itself will supply a little bit of it, but the majority of it in this situation would be coming from that potassium formate because frankly, you just dumped it in. So you just generated a bunch of it really quickly. Other questions? All right, so really what we've been talking about here with common ions, as I've sort of alluded to, is they really are buffers. So let us talk about what a buffer is. A buffer is a solution of one of two things, combinations, either a weak acid and the salt of its conjugate base, or you could have a buffer that is a weak base and the salt of its conjugate acid. They both need to be in the solution to begin with in order for a buffer to exist. You cannot have a buffer that is made up of a strong acid or a strong base. So if you got a strong acid or a strong base there, and you're saying this is a buffer, it is wrong. It is definitely not a buffer. The reason for that is you actually need them to be weak to set up an equilibrium to keep both of those things in solution at the same time, the acid part and the base part of the buffer. In a strong acid or strong base, it is a one-way street where everybody breaks apart. You are not left with the acid there anymore. You're not left with the base there anymore. You have just what's left when it breaks apart. So the essential function of a buffer comes from the idea that it can set up this equilibrium and keep both of those things in solution at the same time. A buffer is actually a solution that can resist changes in pH even when you add more acid or base to the solution. So a very wrong misconception about a buffer is it is a neutral solution, and that is not necessarily correct. A buffer can be a neutral solution, but you can make a buffer pretty much at any pH you like. You can have acidic buffer, you can have basic buffer, and you can have a neutral buffer, just like we did this morning. Yes, pink buffer of 4, yellow a buffer of 7, and the blue solution was a buffer at a pH of 10. Those are all buffer solutions, and obviously that's acidic, basic, and neutral. So you can have a buffer at any pH that you want. What a buffer will do is, let's just say the pH was 4 to start with. If you add some acid to that buffer, and it's a correctly made buffer, and the acid is correctly in terms of this concentration, the pH of that solution after you add the acid will stay around 4. It will go down a little bit because you added some acid. Maybe it goes to 3.9, 3.95, 3.8, but it will not go from like a pH of 4 all the way down to like a pH of 1. You won't see a big jump in pH when you add the acid to it. Same thing if you took that same buffer to start at a pH of 4 and you added base to it, it will go up a little bit. You know, maybe it goes to like 4.1, 4.2, but it will not go from like a pH of 4 to like a pH of 10. So buffers are able to, if they are made correctly, resist really big changes in pH when you add acid or base to it. Any questions on that there? Yeah. Yeah. So buffers are used for different situations, but one particular situation is, for example, let's say you were like working on like a protein or something, right? That's maybe found somewhere in the body or something. That's a specific environment of like a pH of 5 or 3 or something like that. You would make a buffer solution to that, and then you could run your experiment. You know, you could put your protein into that buffer solution, let it equilibrate to it, and then you could kind of run your experiment like it would be in the real conditions and stuff like that. So it's used for that. It obviously is used for situations where we don't want the pH of the environment to fluctuate a lot. So you can make a buffer, you can still add stuff to it, and if you know that pH fluctuation will not affect maybe whatever you're doing and stuff like that. Yeah. Other questions? Okay. So let's talk about really sort of how a buffer actually sort of works to maintain the pH of where it's at. So let us do something here. What do I want to? I'll do it on this page here. Let me clear this page off. So let's first talk about a non-buffer situation and what happens in sort of a non-buffer situation. So we'll take the fine example of water, which by the way is not a buffer for future reference. All right. If we take like a strong acid like hydrochloric acid and we put it into water, because it's a strong acid, we would expect it to 100%, right, break apart into H plus and Cl minus, right? 100%. So what happens when we put something like hydrochloric acid into water, we have just created these ions here, right? And we created a lot of H plus ions really quickly. And we would expect the pH to go down a lot, right? Because basically we just generated a ton of H plus and we would see a pretty significant jump in the pH. So if you had your water at pH of 5 and we add some HCl to it, it would go from maybe a pH of 5-ish all the way down to like a pH of 1. And you see a pretty big jump in pH because that is ultimately what affects the pH, right? If we look at the pH equation, as we were talking about earlier, it is the amount of free H plus in the solution that affects the pH of that. So if we take sodium hydroxide, which is a strong base, and add it to water, we would expect a similar thing to happen. It would 100% break apart into sodium ions and hydroxide ions. So what would we expect to happen in this case? Well, we just created a bunch of OH minus really quickly into that solution, the free OH minus floating around. And what we would see is the concentration of OH minus would go up, which by default means the H plus, which is tied to it, would do the opposite. It would go down, and we would end up with a result of the pH going up. So we would start to see the pH go up. And we would see in this case, again, if say we got some really nice neutral water at 7, and we added a sodium hydroxide to it, we created a lot of this hydroxide. It would go from like maybe 7 to a pH of 11, a pretty big jump in pH because we have a lot of free hydroxide that would occur. First off, any question what happens in a non-buffer situation? Okay, so let's talk about if we take these exact same two guys, this acid and base, but we do not add it to water, let's add it to an actual buffer here. And let's use everybody's favorite buffer example, which is a buffer made up of acetic acid and sodium acetate. How do I know this is a buffer? Acetic acid is a weak acid. Sodium acetate is its conjugate base. They are related to each other. When it says the salt of its conjugate base, that is why the sodium is there, right? Sodium acetate. It's really the acetate part that's related to it. The sodium makes it a salt of its conjugate base. So this is definitely a buffer. And when we think about this buffer, you can think about the acetic acid as obviously the acid part of the buffer, and the sodium acetate here would be the base part of the buffer. So when I take my hydrochloric acid like I did above and I add it to my water, my buffer in this case, the hydrochloric acid is going to react with the buffer. Which part of the buffer would it react with? It would react with the acetic acid or the sodium acetate? It would react with the sodium acetate, right? Because they're acid-base reactions, right? Not acid-acid reactions or base-base. So when we add the hydrochloric acid to this buffer, and again, in this situation, within the beaker, everybody is in there together. This guy is setting up that equilibrium. You got a little bit of H plus, but you have basically your acetate and your acetic acid floating around in the solution to begin with. So it will react with the base part of the buffer, and we're going to get really a double displacement action happening here. Positive, negative, right? The H will come over and it will make acetic acid. The sodium will then come over and say hello to the chloride and make a little sodium chloride action. So this is the reaction that occurs when we add our strong acid to our buffer. So let's talk about a couple of things that we see produced. First off, we did produce some acetic acid. Acetic acid was actually part of the buffer to begin with, right? So it's clearly not going to mess up the pH. And by the way, that always happens when you add an acid to a buffer. You will make more of the acid part of the buffer, and we use up some of the base part of the buffer in the reaction. So you always kind of generate a little bit of the other part of the buffer. That's clearly not going to do anything to the pH. How about our sodium chloride? That is a salt. What type of salt is that? Is that an acidic salt, a neutral salt, a basic salt? That is a neutral salt. Yes, sodium is group 1, so it's neutral, comes from like sodium hydroxide. Chloride comes from, as you can see there, hydrochloric acid, which is a strong acid, which means it's going to be relatively weak and neutral. No reaction with hydrolysis there going on, so it is a neutral salt. But it is actually what we do not see here that we do see in the above equation when we added it to water. What is in the above equation for water that is not here in this situation? What did we produce up here that we did not produce here? Which ion? Yeah, we didn't produce any H plus ions, right? And that's really important for pH. In the water situation, we made a ton of H plus really quickly. That's why we saw a very big jump in pH. But over here, we did not make any more free H plus. So what does that mean? If we didn't make any more free H plus, the concentration of H plus remains relatively constant. Which means if the H plus concentration is relatively constant to where it started at, the pH will also stay relatively constant as well. So in a situation where we add a strong acid to a buffer, the result of that is actually we prevent the formation of free H plus into that solution, which keeps wherever the H plus concentration was at the beginning relatively in the same spot. And that keeps our pH from being a very big jump. I say relatively because if you throw a pH meter in there, you will see the pH go down a little bit. but you will not see a tremendously big jump in pH because of that. So again, here, if you started at 4.74, it maybe goes down to 4.5 or 4.6 or something like that. But again, it will not go from like 4.7 down to like a pH of 1 because of that. Any questions on what's happening in that situation? Now let's take a look what happens when we would add the sodium hydroxide to this guy. I'll go here. We'll squeeze it right there. All right, so if we add our sodium hydroxide to this buffer, which one should it react with? Will it react with the acetic acid or the sodium acetate? It would react with the acetic acid, right? Sodium hydroxide is a base, so it should react with the acid part. And we're going to get a basic acid-base reaction that's going to occur here, which means we're going to create water and some sodium acetate. Now, when we look at this, we see a very similar thing to what we saw in the other reaction. We obviously have made water here, which is not going to mess up the pH. We made the other part of the buffer, which again always happens in this case. So you use up some of the acid part here, the acetic acid, but we make some of the sodium acetate, which again was in the buffer to begin with. So it should not mess up the pH. It is again what we do not see that we do see up here versus here. What do we see up on top that we don't see on the bottom? Yeah, we did not produce in this case any free OH minus. So no free OH minus, right? That means because OH minus and H plus are tied to each other, the concentration of OH minus is relatively the same, which means that the concentration of H plus will also be relatively constant. And because of that, our pH will once again remain relatively constant. So in this situation, when we add the base to the buffer, we prevent the formation of free OH minus, which keeps the H plus concentration constant, keeps the pH also relatively constant as well. Just like in the above there, if you were following this, you will see a slight change in pH, and it should be going in the basic way, going up a little bit. So again, if this was 4.74 to begin with, we added some sodium hydroxide, it would come up maybe, 4.8, 4.9. But again, we would not see it go from like 4.74 to like a pH of 12 when you add a base. Again, because we're pretty much keeping a hold on free OH minus being formed in this case. Any questions on that there? So really the way a buffer is able to function, because it exists as both of those things in solution together, an acid part of the buffer and the base part of the buffer, is able to prevent the formation of free H plus when you add acid, and is able to prevent the formation of free OH minus when you add base. Both of those things keep the H plus concentration relatively constant and keeps the pH being relatively constant, not jumping around. Any questions on that there? Now, so what we do see with this is this sort of situation. If you have a buffer, say this is our buffer. And again, there's sort of an acid part to the buffer and a base part to the buffer. When you add more acid to the buffer, some of the base is going to be used, but you will generate more of the acid part. Dramatically drawn here. And if you add base to this buffer, it will react with the acid part and make more of the base part of the buffer, but use up a little bit of the acid part there of the buffer. So we always sort of regenerate part of the buffer, even though we're adding acid or base to it. And that's what allows a buffer to sort of work over a good range if you make it correctly. There is a limit to sort of the buffer's effectiveness. There's sometimes what is referred to as buffer capacity. So let's say, for example, we didn't read the instructions. I know that would never happen. Or we grab the wrong bottle off the shelf, which is way, way more concentrated than it should be that you need. So let's just say what happens in this case if I just keep adding acid to this buffer. If I keep adding acid, I'm going to keep eating up some of the base, right? And keep eating up some of the base and keep eating up some of the base until there is no more base to be eaten at this point, right? We're full. And if I continue to add acid past that point, what I am essentially doing now is just dumping in a bunch of H+, and you're going to blow through your buffer. And you will, at that point, start to see a pretty big jump in pH because now you're just dumping a bunch of H+ in there. Same thing would happen on the other end if you added just way too much base, right? At some point, you're going to eat up all of your acid part there. And at that point, you would just be dumping in a bunch of OH minus. And again, we should see the pH go up pretty high in that case because of that. So there is a limit to sort of the buffer capacity. When you make a buffer, you want to think about, what type of acid you're adding, the concentration of your buffer, concentration of the acid or base that you may be adding to it. We're going to do a whole lab on that. And, it's really important. Like I said, if you make a buffer, let's say like 0.01 molar, and you grab off the shelf the 18 molar acid instead of like the 0.1 molar acid, and you dump a bunch of it in there, your buffer has not enough moles in there to handle what you're dumping in, and it's just going to blow right through it. So it's really important, the concentration of your buffer, and also obviously the concentration of what you're adding to it. Any questions on that? Buffers are really common ion problems because of that. And this is truly where we do use the Henderson-Hassabalch equation that we were just talking about, is in these situations with the buffer, where again, as well. So as I mentioned earlier, if you were like, okay, I want to make a buffer, say out of hydrochloric acid and some sodium chloride, right? Now, the reason you can't have a buffer that's composed of these two things is when we go to put it into the beaker here together, the HCl will 100% break apart into these two guys, which means in the actual beaker, that is pretty much what you have. That is sodium chloride, right? Which will break apart into sodium and chloride. We'll add some sodium in there and some more chloride, right? So when we look at this, we really don't have an acid part in this solution. We have free floating H+, which is not an acid. We have only the base part in this case, right? Which means it's not going to be effectively going to work as a buffer, because if we add more acid, strong acid, we're just going to build up the H+, right? And you're going to see a big jump in pH. If we add a strong base, it has really no acid to sort of take care of that. So a buffer can never be made up of anything that is strong acid or strong base, because it really won't be able to set up the equilibrium and keep the acid part and the base part in solution in a correct sort of concentration to allow it to effectively work. Now, with that being said, you can absolutely make a buffer from an acid, strong acid or strong base, but the strong acid and strong base is completely gone by the time you actually have made the buffer. What you're left with is a weak acid and conjugate base, or a weak base and a conjugate acid. So you can actually make a buffer from it, but the buffer itself is not made up of the strong acid or strong base. And we'll see an example of that later on in this chapter as well. Any questions on that so far? How buffers function, how they work, why they're able to maintain pH? Here's just a picture of that. Again, it's pretty much what we talked about. In a buffer solution, it keeps that H+ concentration relatively constant. We see a very big jump in pH, as you can see, going from 7 down to like 2 with very little hydrochloric acid added. All right, so which of the following could be buffers? A, B, C. Take a second and think about it. So first off, in order for them to be related to each other, they need to be either a weak acid and basically its conjugate base, or it needs to be a weak base and its conjugate acid. These are really just your Bronsted-Lowry definitions, which means ultimately we're looking at really just a difference of an H plus between them in order for them to sort of qualify per se. So if we look at A, that is HF and potassium fluoride. Potassium fluoride is K plus and F minus. F minus HF, that is a difference of 1 H plus between them. This is why it's called the salt of its conjugate base, because KF makes it the salt. This is a weak acid, HF, and that would be its conjugate base. So this should be a buffer, yes, in this situation. Any questions on that one? How about B here? B is HBr and KBr. This is this basically. So these two guys are a difference of 1 H plus. Is this a buffer? What type of acid is HBr? HBr is actually a strong acid. So is this a buffer then? This is not a buffer because that is a strong acid. So they may be related to each other by 1 H plus, but again, in this case, because it's a strong acid, it won't be able to set up that equilibrium that you basically need for the buffer to work. Lastly, here we got a little sodium bicarbonate and sodium carbonate. What we're really looking at here is CO3 2 minus and HCO3 minus. These two things are related to each other if you take out the sodium. We want to think about where this guy comes from. This guy comes from carbonic acid. Is that a weak or strong acid? Again, if you're not sure, you want to think about that list we've seen a number of times. These are our strong acids, right? Is it one of those guys on that list? It is not. It's actually a diprotic acid. It's a weak acid. And that means that that's probably going to be weak as well. That's like after the first hydrogen came off, right? Ka2 situation happening there. So this would be a buffer. Yeah. Any questions on how to identify buffers and stuff like that, or how buffers function, common ions? Okay, I think we will lay it up there since we don't have enough time to get into some calculations. We obviously will next time.